we'll continue, ladies and gentlemen, sorry, we will continue our exploration of Chem 241 review. And we're going to do a mechanism. We may have done this already. I don't know. This is a peracid. How do you know it's a peracid? Yeah, it's got a peroxide. Peroxide, right? They all have that. Whatever. And per just means extra, right? So, hey, what happens here? What's the driving force for any per molecule reacting? What will happen? Guaranteed for any per molecule. It's got extra oxygen, so motivation, get rid of the extra oxygen, especially if oxygen's bonded to oxygen. And you know that's a bad scenario. Why? Why is oxygen bonded to oxygen a bad scenario? Lone pair repulsion. So that guides your thinking about, yeah, what happens first? I got to attack one of the oxygens so I can break the O bond. And which O do you attack? And I like to talk about the one that's farther from the carbonyl or the one that's closer to the carbonyl. I say distal versus proximal. Distal, more at a distance. And that's the one. Because that's the one where you can resonate all the way to the other O and then protonate the other O. Because when you're done, it would have been nicer if I had showed you the side product. Here it is, free of charge. Because that O on the bottom needs to get an H. So here you go. Arrow 1. Attack O. Distal O. Resonate to make a new carbonyl. Resonate the old carbonyl and pick up a proton. And then the sad part is here, I have to cross my arrows. I'm going to go pink. Which carbon do we come back to? More substituted. Yeah. That says the O makes a bond to the more substituted carbon. It does not say the H makes a bond to the more substituted carbon. Verify that. We clearly have the red arrow with O becoming bonded to H. You are replacing the old bond with a new bond between O and carbon because you can't make a second bond between H and carbon. You know that. You knew that 100 years ago. Okay? And that's the peracid mechanism. It's just 4 arrows and no intermediates. You're done. Bye. 2 points. And what functional group did we make? What critical functional group? Because we use these every test. It's an epoxide. And they get opened up with strong nucleophiles. There's no cations in your thinking. Do you see a cation anywhere? If there was a cation in the ring, you would think more substituted carbon again. But we are not talking about a cation mechanism where we need a C+ to stabilize the O+ with resonance. We're not doing that. This is the one where the nucleophiles got to get to the carbon that's easier to get to. The one that's less sterically hindered. And which of those two carbons, top or bottom in the triangle, is less sterically hindered? Bottom. Attack the bottom carbon, backside attack. Leaving group leaves, but it can't leave because it's attached twice. But the same idea. It looks like an SN2, doesn't it? Backside attack, something leaves that carbon. And we're going to go with a green arrow. And we're almost finished with this. It's a real short activity today. And if the S came from the front side, then the O is left on the back side. Need that lone pair. And where are you going to get a proton from? You need a proton for that. Oh, the ethanol. It'll be the solvent. So even though this is not a great pKeq question, right? pKeq question, because we're going from 17 to 17 basically, right? One alcohol to another. So there's no driving force there. But when you have a solvent as one of the reactants, you have a driving force built in, don't you? It's called Mr. Le Chatelier. There's a huge excess of ethanol driving this equilibrium. So you can use solvents as proton sources when pKeqs are like zero, like close to zero, because it'll drive the reaction. And the O- grabs an H from the excess solvent. And OET- comes off as a side product. If you're curious, you don't need to show me these side products, but they're good for bookkeeping when you're studying. Nice activity. So we'll save that and we'll stop our video. And you